Space sucks. There's no air, no atmosphere whatsoever. The lack of gravity will weaken your muscles, deteriorate your bones, and if you're exposed to it, it will literally boil your eyeballs out of your skull. Going there is an absolutely terrible idea. So of course we're going to do it. Now NASA has an enormous human research program that investigates the effects living in space has on the human body. And one danger of space travel you may not immediately think of is the astronaut's exposure to radiation. We're exposed to radiation every day of our lives, in fact. Natural radiation is everywhere. We have cosmic rays coming from deep space. We have radiation from the sun. There's a radioactive gas called radon that seeps out of the ground. You may actually have seen radon test kits that you can purchase, test these levels in your home to make sure they don't get too high. We even have radiation coming from the food we eat in our own bodies because carbon and potassium, a small proportion of these elements are radioactive and they are in all living things. So a certain amount of natural background radiation exposure is natural and to be expected, and it does not pose a health concern. If we consider 1 year's worth of radiation that we get here in Canada just from our natural background, I'm going to set that equal to 1, represented by the bar here on the left. So some of you recently may have had a CT scan. This is a medical scan that uses X-rays to image your body. During that scan, you would have received almost 3 years worth of radiation all at once. But even in this case, your doctor probably isn't very concerned about any long-term health risks. But when we're talking about radiation exposure during space missions over much longer times at much higher levels, now we are starting to get concerned because 6 months on the ISS is almost 45 years worth of radiation all at once. And for a 3-year mission to Mars, well, you're looking at about 325 years worth of radiation over a single mission. And now this is starting to be a pretty big health concern. That's because exposure to radiation increases your risk of dying of cancer at some point in your life. Now, for our natural background that we're exposed to or the on-medical test, this increased risk is so low that we're not really concerned about it in comparison to all the other genetic and environmental factors our body has to deal with. But the radiation levels experienced over long-term space missions are much, much higher. And as such, we expect that, for example, our 3-year mission to Mars, an astronaut would have an increased risk of dying of cancer by as much as 30% throughout their life. Ionizing radiation is radiation with enough energy to damage living tissue, and it can be either charged or neutral. That's whether or not it carries an electric charge. And these will interact with biological tissue in different ways. And we've gotten pretty good at estimating the long-term health effects of radiation exposure here on Earth, but that becomes a problem in space because of increased amounts of cosmic radiation, often in the form of cosmic rays. These are atoms that have been completely stripped of their electrons, traveling at extremely high speeds originating from deep space. And we have examples of how they interact with cells, and you can see these here on the right. We have a silicon and an iron cosmic ray hitting the cell, and this green light you see here, that's the kinetic energy of the cosmic ray being deposited all along its path as it travels through the cell, just destroying everything in its path. Now, this is really, really bad. However, it could be even worse if that cosmic ray instead strikes equipment surrounding the astronaut, creating secondary showers of radiation, often neutral radiation in the form of gammas and neutrons. Here on the left, we see an example of a cell being bombarded with neutral gamma rays. And here, we don't see the long paths of charged radiation. Instead, neutral radiation deposits all of its energy, all the damage it's going to do at a single point. So the damage is sort of randomly spread throughout the tissue as it's being bombarded. So because these affect tissue differently, we do expect that there will be differences in long-term health effects. So our mission is to measure the charged and neutral contribution to the radiation dose independently from one another. Our satellite will carry our new type of radiation dosimeter into low Earth orbit, and if it does well, future versions of our dosimeter may see use by astronauts for personal dose monitoring. Our payload is able to differentiate charged and neutral radiation dose by anti-coincidence. So here is a schematic of our payload with interacting with a charged particle and a neutral particle. So our payload is made up of 2 detectors, a tissue equivalent proportional counter, that's a sphere of tissue equivalent plastic filled with a tissue equivalent gas. When ionizing radiation passes through it, it generates a current, and from that we can measure the radiation dose. And that is surrounded by an anti-coincidence detector. That's this cap of blue scintillating plastic. This is a type of plastic that glows blue when it interacts with radiation, and that light is collected, and we can detect if it interact with radiation. So what we do is when a radioactive particle hits the tissue equivalent proportional counter, we measure a dose, we check the anti-coincidence detector. If there was a detection event, we know that it was a charged particle that interacted with both detectors. As we saw, it interacts with everything along its path length. But if it was a neutral particle, we won't see a event from the anti-coincidence detector because it is very, very unlikely that a neutral particle would interact with both detectors as it passes through our system. So NEUDOSE is a student-managed team of undergraduate and graduate students. We are about 60 or so engineering and science students, but we do have students from other disciplines because we have many needs, like social media, outreach, recruiting, and we also have our yearly STARS exposition where we showcase the technology we've developed throughout this mission. Thank you very much for listening today. If you would like to learn more about NEUDOSE, you can visit our website at mcmasternewdose.ca or check us out on social media. Thank you.